In the microscopic world, where electrons orbit in visible paths and particles exist in whispers of probability, there lies one of the most profound equations in science, the wave function. It's not merely a mathematical expression, it's the language of quantum mechanics itself, a formula that encodes the very potential of reality. The wave function tells us where a particle might be, but not where it is. It bridges the unseen quantum realm with the observable universe. And yet its meaning has puzzled physicists for nearly a century. Today, we'll unravel the mystery of the wave function, from Schrödinger's revolutionary insight to the mathematics that defines every atom, every photon, and perhaps even consciousness itself. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. The story begins in the early 1920s. Classical physics, the proud foundation of Newton and Maxwell, was beginning to crack. Electrons refused to behave as tiny billiard balls. Light, once thought to be purely a wave, began acting like a stream of particles in the photoelectric effect. Matter itself seemed to oscillate between substance and energy. Enter Erwin Schrödinger, an Austrian physicist with a gift for intuition and mathematics. In 1926, Schrödinger sought to describe how matter waves evolve, not as particles moving through space, but as mathematical waves of probability. He proposed that the behavior of a quantum system could be represented by a function, psi. This simple Greek letter would become the most powerful symbol in quantum mechanics. So what exactly is the wave function? Mathematically, it's a complex-valued function, psi of x, t, describing the amplitude of probability for a particle's position and momentum at any given time. In simpler terms, psi tells us everything that can be known about a quantum system, how it might behave, where it might appear, and how it might interact. But there's a twist. Psi itself isn't directly observable. Only its square, psi squared, gives us something real, the probability density of finding a particle at a given point in space. This principle is known as the Born rule, after physicist Max Born, who interpreted the wave function not as a physical wave, but as a wave of probability. It was a radical idea. Reality, at its most fundamental level, is not deterministic. It's statistical. Nature doesn't tell us what will happen, only how likely it is to happen. Every wave needs an equation, and Schrödinger provided one that changed physics forever. Here, I is the imaginary unit, h is Planck's constant divided by 2 pi, and h hat, the Hamiltonian operator, represents the total energy of the system. This elegant equation describes how the wave function evolves in time. It's the quantum analog of Newton's second law. But instead of describing how a particle moves, it describes how information about that particle spreads through the quantum field. Solutions to this equation, specific forms of psi, correspond to quantized energy levels. For instance, in the hydrogen atom, Schrödinger's equation predicts the discrete electron orbits that perfectly match experimental spectra. Quantum mechanics had found its foundation. The wave function is a complex function, meaning it involves both real and imaginary components. Why? Because quantum behavior isn't confined to one dimension of reality. The imaginary term I allows for oscillations, phase relationships, that make quantum interference possible. When two wave functions overlap, they can either reinforce or cancel each other. This phenomenon, known as quantum interference, lies at the heart of the famous double-slit experiment. Each possible path a particle could take is encoded within psi, but only when observed does one of those possibilities collapse into a definite outcome. This collapse is not part of the Schrödinger equation. It's a mystery still unsolved. Is it triggered by observation? Or does the universe somehow select a single reality among many? While interpretations vary, the mathematics remains unshaken. Every quantum event, from the bonding of molecules to the firing of neurons, unfolds according to the evolution of psi. The wave function isn't limited to single particles. It can describe entire systems, even entangled ones, where two particles share a single combined psi. In entanglement, measurement on one particle instantly affects the other, no matter the distance. This is not because information travels faster than light, but because both particles are part of the same wave function. Extending this idea further, some physicists have proposed that the entire universe has a universal wave function, a mathematical object that contains all possible histories of existence. In this cosmic perspective, every galaxy, every photon, every life form, all are subtle vibrations within the grand wave function of the universe. Visualizing psi is challenging because it exists in complex mathematical space. Yet, in certain systems, like an electron in a hydrogen atom, we can represent psi squared as the electron cloud, the regions where electrons are most likely to be found. These clouds form beautiful symmetrical shapes, s, p, d, and f orbitals, the architecture of the periodic table itself. Quantum chemistry, semiconductor physics, lasers, and superconductors all owe their existence to this invisible mathematical entity. Every quantum computer, every transistor, every LED, operates through the precise manipulation of wave functions. Psi isn't just theory, it's technology. Yet, the wave function also humbles us. It reminds us that reality is probabilistic, that uncertainty is woven into the very fabric of nature. Even with perfect knowledge of psi, we cannot predict an exact outcome, only the likelihood of each. The quantum world defies classical certainty, and in doing so, it invites us to rethink what it means to know. As we continue to explore quantum systems, from computing to cosmology, one truth remains. Behind every measurement, every particle, and every possibility, there is psi, the wave function, the mathematical heartbeat of the universe. In the end, the wave function is more than an equation. It is the story of reality itself, written not in words, but in waves. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about the wave function and how it relates to the greater universe. Join me next time for another deep dive into the strange and unusual world of quantum physics.